Welcome to an example on how to use Stoke's theorem to evaluate a line integral. Here we're given the vector field f and asked to use Stoke's theorem to evaluate the line integral along the curve C of f dot differential r, where the curve C is the intersection of the parabolic cylinder z equals y squared minus x and the cylinder x squared plus y squared equals 9, where the curve C is oriented counterclockwise as viewed from above. So if Stoke's theorem applies, we can evaluate this line integral by evaluating the surface integral shown here. Stoke's theorem states that if S is an oriented surface with unit normal vector n with a piecewise smooth closed boundary C with a positive or counterclockwise orientation, and the vector field f has components p, q, r, which all have continuous partial derivatives, then it is true that the line integral along the curve C of f dot differential r does equal the double integral over the surface S of the curl of f dot n differential s. So under these conditions, Stoke's theorem tells us that the net rotation over the surface S is equal to the net rotation on the boundary C, given these conditions apply. So looking at this graphically, the graph of the vector field f is in gray, and the curve C is the intersection of these two cylinders. We'll notice how the curve C would be the boundary for the surface of the dark blue cylinder inside the light green cylinder, which would be this blue surface here. Looking down on the xy plane, notice how we can see the projection of the surface S onto the xy plane would be this circle. So going back to our work, because Stoke's theorem does apply, we can evaluate this line integral by setting up the surface integral here, which we'll evaluate using this double integral over the region R, where the region R is the projection of the surface S onto the xy plane. But the first step is to write the equation for the surface S. We want the equation in terms of z, where z also equals g of x comma y. Well, the surface S is on the cylinder z equals y squared minus x. So this would be the surface as long as x squared plus y squared is less than or equal to 9. So this also tells us that z equals g of x comma y equals y squared minus x. Now we're also going to need the partial derivatives of g with respect to x and y later, so let's go ahead and find those now. The partial derivative of g with respect to x is a derivative of y squared minus x with respect to x, which is negative 1, and the partial derivative of g with respect to y is a derivative of y squared minus x with respect to y, which is 2y. Now for the next step, let's find the curl of the vector field f, where the curl of the vector field f is equal to del, or the differential operator, crossed with the vector field f. So this cross product would give us this 3×3 determinant, where the first row of the unit vector is I, j, and k, the second row of the differential operators, and the third row of the components of the vector field f. Using expansion by minors, we would get this second line here, where to evaluate the 2×2 determinants, we'll find this product minus this product for each determinant. And notice how these products are actually partial derivatives. So in component form, the s component is a partial derivative of 5y with respect to y, which would be 5, minus the partial derivative of 2z with respect to z, which would be 2. Next, notice how we have a minus here, so minus the partial derivative of 5y with respect to x, that would be 0, minus the partial derivative of xy with respect to z, that would also be 0, comma. For the z component, we have the partial derivative of 2z with respect to x, that's 0, minus the partial derivative of xy with respect to y, that would be x. So simplifying, the curl of the vector field f has an x component of 3, a y component of 0, and a z component of negative x. So going back to our first slide, we now know the curl, and now we have all the information we need. The given surface integral along the closed curve C of f dot differential r by applying Stoke's theorem is equal to the double integral over the surface S of the curl of the vector field f dot n differential s, which is equal to this double integral over the region R, where again the region R is a projection of the surface S onto the xy plane. And remember, the surface is on this cylinder only when x squared plus y squared is less than or equal to 9, which means projecting this onto the xy plane would give us this circle here, centered at the origin, with the radius of 3. So this surface integral is equal to the double integral over the region R of the curl of f, but this curl of f must be expressed in terms of x and y only, because differential a is equal to dx dy or dy dx. So if any of the components of the curl of f had a z in it, we'd have to substitute y squared minus x for z. Notice in this case, though, we don't. So the curl of f is angle bracket 3, comma 0, comma negative x. And then we have dot angle bracket, the opposite of the partial of g with respect to x, which would be positive 1, comma, the opposite of the partial g with respect to y, which would be negative 2y, comma, 1, angle bracket, differential a. Let's go to the next slide and find this dot product. So we'd have the double integral over the region R of 3 times 1, that's 3, plus 0 times negative 2y, that's 0, and then plus negative x times 1. So the integrand function is just 3 minus x, differential a. But again, the region R is this region here inside this circle. So because this region is a circle, let's use polar coordinates to evaluate the double integral. Remember, x equals r cosine theta. So we'll have the double integral over the region R of 3 minus r cosine theta. And then differential a is equal to r dr d theta. And then for limits of integration for r and theta, limits of integration for r will be from 0 to 3, and for theta they'll be from 0 to 2 pi. Let's go and distribute the r. So we have 3r minus r squared cosine theta, dr d theta. And now we integrate this back to r. So we'll have 3 times r squared divided by 2, or 3 halves, r squared, minus r to the third divided by 3 cosine theta, or 1/3 r to the third cosine theta. Performing substitution for r, when r is 3, we have 3 halves times 3 to the second minus 1/3 times 3 to the third cosine theta. And when r is 0, both terms are 0. Continuing on the next slide, here we'll have 27 halves minus, this is going to be 9 cosine theta. And now we integrate respect to theta. So the antiderivative is 27 halves theta minus 9 sine theta. So when theta is equal to 2 pi, we have 27 halves times 2 pi minus 9 times sine 2 pi, minus, when theta is 0, we have 27 halves times 0 minus 9 times sine 0. So simplifying, here we get 27 pi. Well, sine 2 pi is 0. This is 0, and this is 0. So the exact value is 27 pi, which is approximately 84.8230. Remember, this value tells us the net rotation over the surface S, which also equals the net rotation on the boundary curve C. So going back to our graph, because the value we found was positive, because the orientation of the surface is upward, using the right-hand rule, the net rotation will be counterclockwise. Again, using the right-hand rule with an upward orientation of the surface. And this is also true for the curve C around the surface S. The net rotation would be counterclockwise. I hope you found this helpful.